Hi everybody, in this section we're going to be looking at reviewing the intro quiz we had the other day. And the first part is associated with drawing magnetic fields around permanent magnets and the Earth's magnetic field. So I thought I'd maybe go back to the note that we did in class and just review magnetic fields. Remember, magnetic fields exist around anything that is magnetic, so for example a permanent magnet. And you should know a couple of rules about magnetic fields. So the magnetic field lines, they don't really exist, but we use them to help us understand the, the phenomenon of magnetism and interaction of magnetic fields. And what we have here is the magnetic field lines go from north to south, and on the outside and inside south to north, they form a closed loop pattern. And what we usually do is we just usually draw the outside magnetic fields. And the magnetic field is actually 3D, remember. And the other things to remember are when the magnetic field lines are close together, for example at the poles, that's where the ferromagnet is the strongest, and the magnetic field lines never cross. When you're drawing the magnetic field lines, make sure you only draw the outside ones, draw them north to south, draw arrows indicating direction of the magnetic field, and that they do not cross again. So let's take a look at our quiz. So in this situation, the first example here, we got a regular magnet, permanent magnet, and then we draw our magnetic field lines from north to south, like so. I'm just going to draw the outside magnetic field, and put a few arrows on here to indicate the direction of the magnetic field. And that's it. And we're done. If it's a disk magnet, the magnetic poles are on either side, or the top and the bottom. And all you do, just like before, draw the magnetic field lines from north to south to show the direction of the magnetic field. I can draw more magnetic field lines, but you only have to really draw the first one. Now the second situation, or third situation here, we've got two magnets that are interacting. So what you do here, you first draw the magnetic field around each magnet. So do that here, north to south, and then north to south. So this is the internal magnetic field. So north to south again on this side, like so. And what's going to happen is these two magnets are going to be interacting. So we're going to have magnetic field lines going from one magnet to the other. So north to south here, and also another loop going all the way around north to south on the outside as well. So make sure you draw this second set of magnetic field lines as well. We notice all of them go north to south, and they never ever cross. If you cross, that's incorrect. The second question here is asking you to show the direction the compasses would point. Well, all you have to do here is just draw the magnetic field line associated with the magnet. So be like this. So north to south, and the magnets point in direction of the magnetic field. We did this in class. So here the magnetic field is going out. Draw an arrow going out. Then it's going around to the left at the top, and then same at the bottom, just following the magnetic field lines. And here the magnetic field lines go in, so I put an arrow going in. So the compass needle will point in the direction of the magnetic field. Finally, when we're drawing the magnetic field to the Earth, remember our compasses are pointing to the geographic north, which would be up here. So magnetic north would be around here. So a compass is pointing like this, which tells me that it's going actually towards the south pole of a magnet. So the Earth is an upside down magnet, remember. So I'm going to draw the magnetic field lines. I'm going to draw them from north to south, like so. North to south. The other thing to remember is that the geographic pole is fixed, but the magnetic poles move around, and they do not necessarily correspond to the geographic poles. So they're offset a little bit. So here I've got my magnetic north pole. We call it magnetic north pole up here because it's the northern hemisphere, even though it's really a south pole of the magnet. And this would be the geographic north pole. Similarly, at the bottom here, I'd have my magnetic south pole. And here, this would be my geographic south pole. So again, keep that in mind that they do not necessarily correspond, and that the Earth is really an upside down magnet. The next thing I want to review is the domain theory with you. Now remember that certain substances like iron, nickel, and cobalt their atoms can actually become magnetic. They have two slightly magnetic poles, so we call them dipoles. So they're atomic dipoles. They have a north and a south. And what happens with these dipoles, for example, here I've got a cluster of them, they like to arrange themselves in a certain order so that they're all kind of facing the same way. So when you have a whole bunch of these dipoles, atomic dipoles, all facing the same way, we call that little cluster a domain. And the domain will have a north end and a south end that corresponds to the north end of the dipoles and the south end of the dipoles. So remember, make sure you know the difference between an atomic dipole, a single atom, and a domain, which is a cluster of aligned atomic dipoles. Usually what we do is we draw the domains, the cluster, as a little mini magnet. That helps us understand what's going on. Now, and the other thing to remember is only these materials have dipoles and domains. Other materials do not. So the strength of a permanent magnet depends on the relative number of domains that are aligned. So for example, in this substance here, there are a lot of domains that are aligned. So it's a very, very strong permanent magnet. So it has a north pole, south pole. If the substance is unmagnetized, it still has domains, but they tend to be random. Now the other thing that happens is we can also add materials such as carbon. And carbon, when it's added to iron and other substances, hinders the motion and the arrangement and the alignment of the domains. So whatever the domains are aligned in, that's how they tend to stay. So if you make a magnet and it has carbon in it, it makes it harder for the substance to become magnetized, for the domains to become aligned. It also becomes harder for them to become unaligned and get random again. So let's look at the quiz that we had. The two questions were, draw the domains in the following. So first substance was a aluminum bar. There are no domains because aluminum atoms cannot make a dipole. So they never can ever become magnetic. Now iron can have domains. However, if it's unmagnetized, the iron would have domains such that they're all random. So the north maybe at this side, maybe the north might be on this side, a north here, north over here, and let's make one vertical. So you can see here, again, all of the domains are randomly dispersed. They're not aligned. If the bar becomes magnetized, so I can take a magnet and align the domains, they're not all of them, but many of them are facing the same way. So you can see how these domains are all aligned. And I'm indicating the north pole only. You can still do the south. But you can see this end would be the north, and this would be the south end. So again, just be careful. This would be the more domains that are aligned, the more magnetic the substance. And substances that have these domains are called ferromagnetic, and typically they're iron, nickel, and cobalt. Other substances such as aluminum do not have these domains and are not magnetic.